discussion will focus on finding the centroid of plane area by integration. Now, the centroid is actually the geometric center or balancing point of a region R. It is the point where the center of gravity is located. So, let us say we have a sphere. The center of the geometric center, rather, or the centroid of a sphere is at the core or at the center of the sphere. Now, another example is if we have a rectangular box, how do we find the centroid or the geometric center of a rectangular box? It is actually the intersection at the intersection of the diagonals of a rectangular box. And the centroid of a mass, which is a point such that the first moment the mass with respect to any plane is the same as if the whole mass were concentrated at that point. So typically, for a plane, it will work in the same manner. Now, let us say we have a circle. Of course, if we have a circle, let us say that this is the circle, the centroid of the circle is at the center of the circle. This is the geometric center of the circle, and this is where the center of gravity is. Okay, now if we have a rectangle, okay, the question is how do we find the, how do we find the centroid of the rectangle? Now, to determine the centroid of the rectangle, we simply draw the main diagonals of the rectangle. Now, the intersection of the main diagonal of a rectangle is where the centroid is. And this will play important role in finding the centroid of plane area by integration. Okay, so we will let the coordinates x bar, y bar be the centroid of the region R. So x bar is the x coordinate and y bar is the y coordinate of the centroid, okay, of the region R. And since in integration we use rectangular element, we will let x sub c, y sub c be the centroid of a typical element of the region R. Hence, if we want to find x bar and y bar for a plane area, x bar is the moment with respect to the y-axis over the area. Now, the moment with respect to the y-axis is determined by simply multiplying the distance of the centroid of the typical element from the y-axis and multiplying it by the differential of a. Now, if we are going to evaluate the integral within the limits of integration, then that will give us the moment with respect to the y-axis. Or we can simply say that the moment with respect to y-axis is the integral of the product of x sub c and the differential of a within the limits of integration. And x bar, which is equal to moment with respect to y-axis over the area, is equal to the integral of x sub c times the differential of a over the integral of the differential of a. Of course, the differential of a can be determined by the method that we had discussed before. Okay, finding the area under the curve and finding the area between curves. Now, what about y bar? Y bar is the moment with respect to the x-axis over the area. And the moment with respect to the x-axis is computed by getting the integral within the limits of integration of y sub c times the differential of A. Now, y sub c is the distance of the centroid of the element from the x-axis. Now, if we want to get, the centroid of the area between curves, okay, we are going to consider the area between curves. Let us say we have in the first figure, okay, the area is bounded above by, say, y is equal to f of x, and below by y is equal to g of x. Of course, we will call this as y sub h, and we will call this as yn. Okay, the upper curve and the lower curve. Now, if we have if we are considering the region R, okay, bounded by y sub h, which is equal to a function of x, and y sub l, which is also a function of x, it is equal to g of x. And if we are going to use a vertical element, then if we are going to locate the centroid of the element, it will be approximately here. It is the intersection of the diagonals of the element. So this point is the point whose coordinates are x sub c, y sub c. Okay? Now, x sub c is the distance of the point from the y-axis, and y sub c is the distance of the point from the x-axis. Okay, now, if we will determine the value of x sub c, since this point has the coordinates x, y, h, and the lower point has the coordinates x, y sub l, then x sub c is equal to x. Okay? Therefore, if we will get the moment with respect to the y-axis, the moment with respect to the y-axis is equal to the integral of x sub c times the differential of a. So now, since x sub c is equal to x, then the moment with respect to the y-axis is equal to, okay, x sub c is x, the distance of the centroid of the element from from the y-axis rather. So we can replace x sub c by x and then just multiply this by the differential of a. So the differential of a, of course, is y sub h minus y sub l, upper minus lower times dx, which is the thickness of the element. Okay, so x times y upper minus y lower times the differential of x, and we simply evaluate this from the lower limit a to the upper limit b, or we can say from the lower limit c to the upper limit d. Okay, so let us just say that we are evaluating the integral within the closed interval from a to b. So lower limit is a and upper limit is b. Okay, now take note that the differential of a here is the length of the element YH minus YL. Okay, recall the discussion on area between curves times the thickness, which is the differential of x. Now, if we will get the moment with respect to x-axis, then the moment with respect to the x-axis is actually y sub c, the distance of the centroid of the element from the x-axis, times the differential of a. But what is y sub c? Now, if we want to get y sub c, okay, y sub c is actually equal to 1/2 of y upper minus y lower. Okay, this point is the distance from the x-axis. So to get the distance of this point from the x-axis, we simply get 1/2 of y upper minus y upper plus y lower. We get the average, no? Okay, therefore, if y sub c is equal to 1/2 of y upper minus y lower, okay, from the lower limit a to the upper limit b, then this is equal to 1/2 integral of y upper plus y lower, okay, and the differential of a is y upper minus y lower times the differential of x. Take note here that we have sum and difference of two numbers, yh plus yl times yh minus yl is equal to the difference of the squares of the two numbers. Okay, therefore, this will give us 1/2 integral from a to b of y upper square minus y lower square times the differential of x. So this is the moment with respect to the x-axis if we have a vertical element and the region is bounded by the two curves. Now, on the other hand, if, excuse me, okay, if this time, if we have the region bounded by two curves on the right and on the left, okay, let us say that we have this point whose coordinates are x, r, y. And this point has coordinates x sub l, y. So the distance of this point from the y-axis is xr, and the distance of this point from the y-axis is xl. Remember the discussion on finding the area between curves when bounded by two curves on the right and on the left. Okay, now, of course, the thickness of the element is the differential of y, therefore the differential of a, okay, the differential of a is equal to xr minus xl times the differential of y. Now, if we want to locate the centroid of the element, this is where the centroid of the element is. It is where the two diagonals meet or intersect. So this point will have the coordinates x sub c, y sub c. Y sub c is the distance of the centroid of the element from the x-axis, and x sub c is the distance of the element from the y-axis. Now, at this time, no, y sub c is equal to y. It is a distance of the centroid of the element from the x-axis. But x sub c this time is x sub c is equal to 1/2 of xr plus xl. So this is equal to 1/2 of xr plus xl. Therefore, if we will get the moment with respect to x-axis, the moment with respect to the x-axis is the integral of, okay, the distance of the centroid of the element from the x-axis, which is y sub c, times the differential of a, and the moment with respect to the x-axis, okay, from a to b is equal to the integral from a to b of y sub c is y times x sub r minus x sub l times the differential of y. Okay, this is it. Okay, now what about the moment with respect to y-axis? The moment with respect to the y-axis is the integral of x sub c times the differential of a, limits going from, okay, let's make this c to d. Okay, we will evaluate the integral within the interval from C to D. So limit going from C to D. Okay, therefore, the moment with respect to y-axis, since x sub c is 1/2 of xr plus xl, so we will have 1/2 integral from c to d of x sub r plus x sub l, and the differential of a is x sub r minus x sub l times the differential of y. Now, we have again sum and difference of two numbers here, and getting the product will give us the moment with respect to y-axis is equal to 1/2 of the integral of x sub r squared minus x sub l squared times the differential of y, limits going from c to d. So this is how we compute for the moment with respect to y-axis when the element is horizontal. It is equal to 1/2, okay, times the integral of x sub r squared minus x sub l squared times the differential of y, okay, evaluated within the limits of integration. Okay, now, to illustrate how to find the centroid of area under the curve and centroid of area between curves, now we are going to use or illustrate it using some examples, but this time we are going to use the whiteboard. So let me stop sharing the PowerPoint. Okay, so for the first example, we will find the centroid of the area under the curve y is equal to x squared from x is equal to 2 to x is equal to 4. Of course, before anything else, we need to sketch the region bounded by the given curves, okay, within the given interval. Okay, so if we have y is equal to x squared from x is equal to 2 to x is equal to 4, we need to get the intersection of the curve y is equal to x squared, which is a parabola opening upward with vertex at 0, 0. Okay, we need to get the corresponding value of y for given values of x is equal to 2 and x is equal to 4. So when x is equal to 2, then y is equal to 2 raised to the second power, and y raised to the second power, of course, is, okay, excuse me, y raised, 2 raised to the second power is equal to 4. So we will have a point of intersection at 2, 4. The parabola will intersect the vertical line x is equal to 2 at 2, 4. On the other hand, when x is equal to 4, then y is equal to 4 raised to the second power. Therefore, y is equal to 16. Hence, another point of intersection at 4, 16. The parabola will intersect the line x is equal to 4 at 4, 16. Now, if we are going to show this geometrically, okay, let us draw the curve. We have the y-axis, and let us draw the x-axis. Okay, now let this be 1, 2, 3, 4. Okay. And let us locate the points of intersection. Now, since y is equal to 16 here on the second intersection, we can just let one division of the y-axis be 4. So one division is equivalent to 4 units. So if we have 2, 4, this is the point 2, 4, and we have 4, 16. This is 4, 8, 12, 16. Okay, therefore, the other point of intersection is at 416. This is 416. So we can now draw the two vertical lines. Okay, this is the line x is equal to 2. And here we have the vertical line x is equal to 4. So we can now draw the parabola. Of course, the parabola y is equal to x squared is a parabola opening upward with vertex at 0, 0. Of course, this does not form part of the region. So I just draw broken line here. And we will just consider that part of the parabola y is equal to x squared, from x is equal to 2 to x is equal to 4. Okay, so we are interested with this region. The region under the curve y is equal to x squared. Okay, next we can now draw the element, the representative element. Of course, it will be more convenient if we will use the vertical element, since if we will draw the vertical element consistently, it is always bounded above by y is equal to x squared and below by the x-axis. So drawing the vertical element, the anywhere within the region R, okay, let us say that this is the element. Of course, the two ends of the element touches the boundary. The x-axis, okay, thickness is dx, and this point is on the parabola y is equal to x squared, and coordinates of this point are xy. Okay, and we can now get the area of the element. Okay, we need to get the area of the element to compute for x bar and y bar. So if we will get the area of the element is equal to the length. Of course, the length is equal to y, okay, and the thickness is dx. Okay, so the area of the element is equal to y dx, the length times the thickness. And if we will evaluate this within the limits of integration, of course, we are going to consider the closed interval from 2 to 4. Variable of integration is x, therefore, the limits of integration will be from x is equal to 2 to x is equal to 4. Hence, the lower limit is 2 and the upper limit is 4. And since the variable of integration is x and y, the integrand is still in terms of y, then we have to express y in terms of x. And since y is equal to x squared, then we have to replace y by x squared. So times the differential of x, limits going from 2 to 4. Therefore, integrating, the integral of x squared dx is x cubed over 3. And we have to evaluate this from the lower limit 2 to the upper limit 4. Okay, now we can bring out 1/3 and just evaluate x cubed from the lower limit 2 to the upper limit 4. Therefore, it gives us 1/3 times x cubed when x is equal to 4 is 4 raised to the 3rd power minus the value of x cubed at the lower limit, x is equal to 2. So we will have 2 raised to the 3rd power. Hence, it gives us 1/3 times the quantity 4 raised to the 3rd power is 64 minus 8. Okay, therefore, the area is equal to 56 over 3. Okay, so the area of the region is 56 over 3 square units. Okay, now since we need to find the centroid x bar, y bar, okay, we have to determine first the moment with respect to the x-axis and the moment with respect to the y-axis. And to get the moment with respect to the x-axis, we need to locate the geometric center of the representative element, which is at the intersection of the diagonals of the element. So this point, okay, approximately is where the centroid of the element is. Okay, coordinates of the centroid of the element are x sub c, which is the distance from the y-axis, y sub c, which is the distance of the centroid of the element from the x-axis. Now, geometrically, if we want to get x sub c, which is the distance of the centroid of the element from the y-axis, x sub c is equal to x. Okay, and y sub c, which is the distance of the centroid of the element from the x-axis, is 1/2 of the length of the element. Now take note that the geometric center of a rectangle, if we have a rectangle, the geometric center is at the intersection of the diagonals. This is where the geometric center is. This is x sub c, y sub c. And if we have the x-axis here and the y-axis here, okay, the length of the element is y, hence x sub c, y sub c, the centroid of the rectangular element, is exactly midway between the upper and the lower end. Okay, and since the length of the element is y, then y sub c is equal to 1/2 of y. Okay, let me erase this. And let us continue here. So y sub c, which is the y coordinate of the centroid of the element, is the distance of the centroid of the element from the x-axis, and this is 1/2 of the length of the element. So 1/2 of y. Therefore, if we will solve for the moment with respect to x-axis, the moment with respect to the x-axis is the integral of the distance of the centroid of the element from the x-axis, and that is y sub c, times the differential of a. And we will evaluate this from the lower limit 2 to the upper limit 4. Now, y sub c is 1/2 of y. So 1/2 times the integral from 2 to 4 of y sub c. Y sub c is y, and the differential of a is y dx. Y times the differential of x from the computation of the area. Hence, simplifying gives us moment with respect to the x-axis is 1/2 integral from 2 to 4 of y squared times the differential of x. Now, of course, the curve is y is equal to x squared. So replacing y by x squared will give us x squared raised to the second power times the differential of x, which will give us 1/2 of the integral from 2 to 4 of x to the 4th times the differential of x. Of course, the integral of x to the 4th dx is x raised to 5 over 5. Okay, and this must be evaluated from 2 to 4. If we will bring out 1 over 5, then we have 1/2 times 1 over 5. And we will just evaluate x raised to 5 at x is equal to 4, the upper limit. So we have 4 raised to the 5th power minus, okay, x raised to 5 at the lower limit 2 is 2 raised to the 5th power. And simplifying will give us 1 over 10, okay, times 4 raised to the fifth power minus 2 raised to the fifth power. Okay, what is 4 raised to the fifth power? Okay, wait. My pen is not working. Let me fix it first. Okay. 4 raised to the fifth power is 1024, 1024. And 2 raised to the fifth power is 32. Okay. So this will give us moment about the x-axis is equal to 9, okay, 998. So this will give us 496 over 5. 496 over 5, moment about the x-axis. Then, we compute for the moment about the y-axis. So, moment about the y-axis this time is the integral of x sub c times the differential of a. It is equal to the distance of the centroid of the element from the y-axis, and that is x sub c. Okay, limits going from 2 to 4, and x sub c is x. Therefore, this is equal to the integral from 2 to 4, replacing x sub c by x, times the differential of x. The differential of x is y dx. Hence, this will give us the integral from 2 to 4 of x times y is x squared times the differential of x. Therefore, moment with respect to y-axis is the integral from 2 to 4 of x cubed times the differential of x. And evaluating the integral will give us x to the fourth over 4. And this must be evaluated from the lower limit 2 to the upper limit 4. And let us bring out 1 over 4 and evaluate x to the fourth at the upper limit. So we have 4 raised to the fourth power minus 2 raised to the fourth power. Okay. So this will give us 1 over 4. Now, what is 4 raised to the fourth power? 4 raised to the fourth power is 256. Okay. 256, and 2 to the fourth is 16. 256 minus 16 is, of course, 240. Dividing it by 4 will give us 60. So moment about the y-axis is 60. Okay, so we're done with the moment about the x-axis and moment about the y-axis. And we can now get x bar and y bar. X bar is equal to the moment about the y-axis over the area, and y bar is the moment about the x-axis over the area. Now, the moment about the y-axis is 60, and the area, computed area, is 56 over 3. Okay, therefore, if we will do the computation, dividing 60 by 56 over 3 will give us x bar is equal to 45 over 14. This will give us 45 over 14. Okay. And y bar which is equal to moment with respect to the x-axis, okay, over the area. Moment with respect to the x-axis is 496 over 5 over the area. The area is 56 over 3, okay. Therefore, this will give us y bar is equal to, I think this is 186 over 35. Okay. Since 56 is divisible by 4, right? This is also divisible by 4. So that will give us 186 over 35. Okay, so we have x bar. Okay, let me use a different color here. So x bar, y bar, the coordinates of the centroid of the region has the coordinate x bar 45 over 14, and y bar is 186 over 35. Now, if we are going to locate 45 over 14, 186 over 35, okay, approximately 45 over 14 is 3.2, just for plotting purposes, 3.2. And 186 over 35 is approximately, this is approximately 5.3. Okay, therefore, if we are going to locate the centroid of the region at 3.2, 5.3, okay, we have 1, 2, 3.2, 5.3, approximately it will be here. This one, the yellow point, approximately. This is where the centroid of the region is. Okay, let me use the black one, okay, to locate the centroid of the region. This is approximately where the centroid is. So this black point has the coordinates x bar, y bar. It is where the geometric center of the region lies. Okay, so that is how we get the centroid of the area under the curve. Okay, of course, before anything else, we need to draw or sketch the region. Then we draw the element. We find the area, the integration. We find the moment with respect to the x-axis, which is the distance, the integral of the distance of the centroid of the element, y sub c, okay, from the x-axis times the differential of a. Moment with respect to y-axis is the distance of the centroid of the element from the y-axis times the differential of a, and then evaluate the integral within the limits of integration. Then to get x bar is the moment with respect to y-axis over the area, and y bar is the moment with respect to the x-axis over the area. So that gives us the coordinates of the centroid of the region, the geometric center of the region R. Finding the centroid of the region bounded by two curves. So let us consider the second example. We need to find the centroid of the area bounded by y is equal to 4x squared minus, y is equal to 4x rather, minus x squared, and the line x plus y is equal to 4. And since we need to sketch first the curve, we need to get the intersection of the two curves. Y is equal to 4x minus x squared. This is a parabola opening downward. And x plus y is equal to 4. If we will solve these two equations simultaneously, then let us just call this as equation number 1. And this one is, if we will solve for y, is 4 minus x. And let us call this as equation number 2. Okay, excuse me. So solving the two equations simultaneously by substitution, from equation number 1 is y is equal to 4x minus x squared. If we will replace y by 4 minus x, then 4 minus x is equal to 4x minus x squared. Transposing the right member to the left side gives us x squared minus 4x plus 4 minus x is equal to 0, which can be simplified as x squared minus 5x plus 4 is equal to 0. Now, factoring the left member, factors are x minus 1, x minus 4 equated to 0, and equating each linear factor to 0 will give us x equals 1 and x is equal to 4. Now, since y is equal to 4 minus x, okay, let me write here, y is equal to 4 minus x, that is equation number 2. When x is equal to 1, then y is equal to 4 minus 1, or y is equal to 3. Therefore, we have a point of intersection at 1, 3. And when x is equal to 4, y is equal to 4 minus 4, hence y is equal to 0. Another point of intersection at 4, 0. So these are the points of intersection. Okay, so we can now sketch the curve, okay? Or maybe we can determine the vertex of the parabola. If we have the parabola y is equal to 4x minus x squared, we can write this in the standard form. X squared minus 4x is equal to negative y. So completing the square in x, we have to add 4 to both sides of the equation. The left member is now a perfect square trinomial whose factors are x minus 2 square. And the right member, we can factor out the negative sign, giving us y minus 4. Therefore, we have now the standard form of the equation of the parabola, opening upward, vertex at 2, it is opening downward because of the negative sign here. Pardon. Okay, so vertex at 2, 4, and it opens downward. Hence, we can now draw the region. Okay. Let this be the y-axis, and let this be the x-axis. Intersection of the two curves at 4, 0. Okay, let this be 1, 2, 3, 4. This is 4, 0. And 1, 3. 1, 2, 3. Another point of intersection at 1, 3. Okay. So we can now draw the line, the second, which is the representation of the second equation. Okay, this is the line. X plus y is equal to 4. Excuse me for a while. Now, if we are going to solve for y, then y is equal to 4 minus x. And this time we can now draw the parabola opening downward, vertex at 2, 4. Approximately, this is where the vertex is. And the parabola will intersect the curve, the line rather, at the 2 points of intersection. This is the parabola. Y is equal to, and we are referring to this region, the region. Now, first we need to find the area of the region. So to find the area of the region, okay, it will be more convenient if we will use the vertical element, since the region is bounded by the two curves above and below. Above by the parabola and below by the line. Okay, let this be the region, element, the representative element. Okay, of course, this point will have the coordinates x, y upper, since it is bounded by the parabola. We will call this as YH. And this one has the coordinates x, y lower. Okay, so we shall call this equation as YL. YL is equal to 4 minus 4 minus. Okay, so to find the area, how do we find the area? The area is equal to, okay, let me use again the area is equal to, it is based on the area of the element, the length y. Of course, y is equal to y upper minus y lower, since it is bounded by the two curves above and below. So y upper minus y lower, and the thickness is the differential of x. And we are going to evaluate this from x is equal to 2, x is equal to 1 to x is equal to 4. We are considering the closed interval from 1 to 4. Okay, from x is equal to 1 to x is equal to 4. So the limits of integration are 1, lower limit 1, upper limit is 4. Now, what is the area? Area is equal to the integral from 1 to 4. Of course, y upper is 4x minus x squared. So 4x minus x squared. And y lower is 4 minus x. Upper minus lower times the thickness differential of x. If we will simplify this, then we have the integral from 1 to 4 of, okay, 4x minus x will give us 5x minus x squared minus 4 dx. Hence, evaluating the integral gives us integral of 5x dx is 5x squared over 2 minus x cubed over 3 minus 4x. And we need to evaluate this from the lower limit 1 to the upper limit 4. So we will have, okay, let's have a brace here. Okay, when x is equal to the upper limit 4, that will give us 5 times 4 raised to the second power over 2 minus 4 raised to the third power over 3 minus 4 times 4. Okay, minus the value of the integral of the lower limit 1. So 5 times 1 square over 2 minus 1 raised to the third power over 3 minus 4 times 1. And if we will compute this, okay, if we will compute this, then this will give us the area is equal to 9 over 2 square units. Okay, you just check the computation, okay? So area is equal to 9 over 2 square units. So we're done with the area, but we need to find the centroid of the region R, the centroid of the region bounded by the parabola and the straight line. So before we compute for the centroid, we need to locate the geometric center of the element. So the geometric center lies somewhere here. This point will have the coordinates x sub c, y sub c. Okay. Earlier, we were able to show how to get x sub c and y sub c in terms of x and y lower if the element is vertical. Now, x sub c is the distance of the centroid of the element from the y-axis. Therefore, x sub c is equal to x. This is the distance of the centroid of the element from the y-axis. Now, y sub c is the distance of the element from the x-axis. So this is equal to 1/2 of y upper minus y lower. Okay? Hence, if we will get the moment with respect to the y-axis, this is equal to the distance of the centroid of the element from the y-axis, which is x sub c, and we will multiply this by the differential of a and evaluate within the limits of integration from 1 to 4. Now, since x sub c is equal to x, so we have the integral from 1 to 4 of x times the differential of a. Now, the differential of a is YH minus YL here. Okay? So this is Y upper minus Y lower times the differential of X. And if we will substitute Y upper minus Y lower times the differential of X in the simplified form, then we have the integral from 1 to 4 of X times. Now, Y upper minus Y lower in the simplified form is 5x minus x squared minus 4. So just multiply this by 5x minus x squared minus 4 times the differential of x. Hence, this gives us the integral from 1 to 4 Okay, multiply 5x minus x squared minus 4 by x, and that gives us 5x squared minus x raised to the third power minus 4x dx. Okay, giving us the integral equal to 5x raised to the third power over 3 minus x to the fourth over 4 minus 4x squared over 2. Now, 4x squared over 2 is 2x squared. 4 over 2 is 2. So we have here 2x squared. Then evaluate this from 1 to 4. Hence, we will have the value of the integral at the upper limit 4 is 4 raised to the third power over 3 minus 4 raised to the fourth power over 4 minus 2 times 4 raised to the second power, okay, minus the value of the integral at the lower limit 1. So 5 times 1 raised to the third power over 3 minus 1 raised to the fourth power over 4 minus 2 times 1 raised to the second power. Okay. And if we will compute for the moment with respect to the y-axis, the moment with respect to y-axis is 45 over 4. So just do the computation. No? So moment with respect to y-axis is 45 over 4. Now at this point, we can now actually solve for x bar, since x bar is equal to the moment with respect to y-axis over the area, then this will give us 45 over 4 over the computed area. The computed area is 9 over 2. Therefore, x bar is equal to 5 over 2. 5 over 2. Okay, so we already have the value of x bar. Our problem is to get y bar. And to get y bar, we need the moment with respect to the x-axis. And take note that the moment with respect to the x-axis is y sub c times the differential of a. And take note that y sub c is 1/2 of yh minus yl. And the differential of a is yh minus yl. So the moment with respect to the x-axis is yh squared minus yl squared. Well, anyway, let us show it in the next page. Now, y sub c is 1/2 of y upper plus y lower. And the differential of a is equal to y upper minus y lower times the differential of x. Therefore, if we will compute for the moment with respect to x-axis, which is equal to the integral from 1 to 4 of yc. Yc is 1/2 of y upper plus y lower times the quantity y upper minus y lower times the differential of x. Okay, this is actually moment with respect to the x-axis is equal to the integral of y sub c times the differential of a. Hence, this is equal to the integral from 1 to 4 of 1/2. Okay, yh plus yl times yh minus yl is yh squared minus yl squared times the differential of x. Okay, and this is actually the formula given to get the moment with respect to the x-axis when the region is bounded by two curves above and below, and we use the vertical element. So moment with respect to the x-axis is 1/2 of the integral within the limits of integration of yh square minus yl square dx. Now, but what is yh square and what is yl square? Now, let us refer to the previous slide. YH is determined by the parabola, and the parabola is y is equal to 4x minus x squared, and YL is determined by the line x plus y is equal to 4, or YL is 4 minus x. So we have y is equal to 4x minus x squared, and y is equal to 4 minus x. Excuse me. So let's go back to the slide. Okay, so let me write here. Y upper is determined by the parabola y is equal to 4x minus x squared, and y lower is x plus y plus 4, so y is 4 minus x. Okay. So substituting will give us 1/2 of the integral from 1 to 4 of, okay, y upper is 4x minus x squared raised to the second power minus YL is 4 minus x raised to the second power dx. Of course, we need to simplify first. Okay, 1/2 integral from 1 to 4 times. Let us get the square of 4x minus x squared. And that gives us 16x squared minus twice the product, so minus ax cubed plus x raised to the 4th power minus the product, the square of 4 minus x, which is 16 minus ax plus x squared. Okay, and simplify further gives us 1/2 integral from 1 to 4 of, okay, we have 16x squared minus x squared, and that will give us 15x squared. And minus 8x raised to the 3rd power plus x to the 4th minus 16 plus ax times the differential of x. So let me check again. We have 16 minus x squared is 15x squared minus 8x cubed plus x to the 4th minus 16 minus 8x. Then we evaluate the integral. So we have 1/2. Integral of 15x squared dx is 15x cubed over 3. 15 by 3 gives us 5. 5x cubed minus integral of 8x cubed dx is 8x to the 4th over 4. So 8 by 4 will give us 2. X to the 4th plus x raised to the 5th over 5 minus 16x plus integral of 8x dx is 8x squared over 2. So we will have 4x squared. And we need to evaluate this from 1 to 4. Hence, evaluating the integral from the lower limit 1 to the upper limit 4 gives us 1/2 times the value of the integral at the upper limit 4 gives us 5, 4 raised to the 3rd power minus 2, 4 raised to the 4th power plus 4 raised to the 5th power over 5 minus 16 times 4 plus 4 times 4 raised to the 2nd power minus the value of the value of the integral at the lower limit 1. So 5 times 1 cubed minus 2 times 1 to the fourth plus 1 raised to the fifth power over 5 minus 16 times 1 plus 4 times 1 square. Close bracket, close brace. And if we will do the computation, this will give us the moment about the x-axis is equal to 54 over 5. Okay, so just do the computation using your calculator. So moment with respect to the x-axis is 54 over 5. Hence, we can now compute for a y bar. And y bar is equal to the moment about the x-axis or with respect to the x-axis over the area. Moment with respect to the x-axis is 54 over 5 over, the area is 9 over 2. Okay, so 12 over 5. Y bar is 12 over 5. Okay, hence, x bar, I think, is 5 over 2. So x bar, y bar is 5 over 2, 12 over 5. This is where the centroid of the region is, the region R is. So 12 over 5. So going back, we have here x bar is equal to 5 over 2. And we were able to determine y bar. Y bar is 12 over 5. Therefore, x bar, y bar has the coordinates 5 over 2, 12 over 5. And if we will locate that on the region, 5 over 2 is 2.5 and 12 over 5 is 2.4. Okay, so 2.5, 2.4. So approximately, this is where the centroid is. The black point. The centroid whose coordinates are x bar, y bar. At 5 over 2, 12 over 5. So approximately this will be the center or the geometric center of the region. So there we were able to show how to find the centroid of a plane area, okay, by considering an example where the area is under the curve, and the second example is the region R is bounded by the two curves above and below. Okay, in our next discussion, we will consider finding the centroid of solid of revolution.